Suppose you have a linear equation in two or more variables. Since the equation has more than one variable, there will be an infinite number of solutions. If we insist on the solutions being integers, we have a linear Diophantine equation. These are named after Diophantus, a Greek mathematician who probably lived around 100 AD. But Diophantus actually studied quadratic equations with rational, not integer, solutions. So Diophantus didn't ever study what we now call linear Diophantine equations. So suppose a, b, and c are integers, and we want to find an integer solution, xy, to the equation. A necessary condition is that the greatest common divisor of a and b must divide c. But if this is true, we can divide through by the greatest common divisor to get an equation of the form where the greatest common divisor of our new coefficients is 1. So we can assume that we're starting with such an equation. So let's consider an equation where the greatest common divisor of our coefficients is 1. We've already shown that this equation will have integer solutions in a rather ugly form. So remember, aesthetics matter. Can we improve the look of the solution? Well, suppose x0, y0 actually is a solution to our linear equation. How can we find another solution? Remember, you can assume anything you want as long as it's explicit. So, suppose x prime, y prime is another solution. Now, since x0, y0, and x prime, y prime are both solutions, they have to satisfy the equation. And if we subtract one from the other, we get but this means that if we take this equation mod A and mod B, we get, and continuing our assumption that the greatest common divisor of A and B is 1 means that B inverse mod A and A inverse mod B both exist, and so we can remove those factors and we get, and so that tells us that y naught is y prime plus some multiple of a, and x naught is x prime plus some multiple of b. But since y naught, x naught are solutions, then they have to fit into the equation. But since x prime, y prime was also a solution, we know that ax prime plus by prime was d, and so we can simplify, which we can solve for either s or t. Let's go ahead and solve that for s. And this gives us the following theorem. Suppose we have a solution to a linear Diophantine equation. Then a general solution will be, where you can view this as our solution plus a b multiple of t and y minus an a multiple of t. And this gives us another way to solve linear Diophantine equations. So let's try to find all solutions to 3x plus 7y equals 11. So we still need to go through our initial congruences. We find that 3x is congruent to 11 mod 7, 7y is congruent to 11 mod 3, and so we can reduce them. And in this case, we have a nice simple solution. From the second congruence, we'll know we'll get a solution of the form y equals 2 plus a 3 multiple of t. So if we let t equal 0, we know that y equals 2 will be a solution for some value of x. But since 3x plus 7y is 11, we know that if y equals 2, then x has to be negative 1. So one solution is y equals 2, x equals negative 1, and our general solution, we'll take our x value, we'll add 7 times t, we'll take our y value and subtract 3 times t. Or let's try to find a general solution to this linear Diophantine equation. So we get the congruences. The second congruence with the smaller modulus has solutions corresponding to the equation 5y minus 7z equals 6. So I can solve the original problem by finding integer solutions to 5y minus 7z equals 6. But we can solve that equation by solving the congruences, which we can reduce, where, again, our second congruence has solutions corresponding to the equation 3z minus 5w equals 1. And so that's the second equation we want to find integer solutions to. But we can solve that equation by solving the congruences, where we finally reduce down to a simple congruence, w congruent to 1, and so we know w equals 1 is a solution. But once you know w, you can find all the other variables. And so we find so x equals negative 5, y equals 4 are solutions to the original Diophantine equation, and we can add 12, the coefficient of the other variable, and subtract 7, the coefficient of the other variable, to get our general solution.